I'm back with the cosmic ray experiment. So today I want to show you the stuff I've done so far. So we have this and this, which are new. So I'll get into this first. This is what's known as a peak detector. You can see we have a diode there, capacitor there, and the resistor I'm not using as a resistor, just a lead to hook up the ground to. Okay, so the peak detector, as you're going to see in a second, I'm going to show, probably interject into this some clips of me talking with the oscilloscope. Sorry for the camera again, that I have a tripod, ordered a tripod, and it hasn't come yet, so a few another months maybe, because it's coming, it's going to take a while. Anyway, so that's the peak detector. I'm just using a, let me see, 101 cap, which is 100 picofarads, so, and just a tiny little diode, glass diode, so pretty small, but it works because the pulses are so short, they just need to be elongated a little bit. And then some of you may recognize this. This is an opto-isolator. Okay, what it is, it's an LED and a phototransistor, just packaged up inside one nice little tight package. And this is good because basically what it does is it uses the light to get a signal through. So you can sort of send analog type signals. Oh, digital is better, but analog type signals. And they don't have to be electrically connected at all because they're connected optically, hence the opto-isolator term. So I have the signal out of the peak detector coming in through this resistor to protect the input LED. And then the cathode goes to ground. And on the other side, what I have this done is the transistor has its input here, so the collector is basically where the scope probe is. The emitter is that gray cable that's going off to ground on the oscilloscope. Oops. That got disconnected. And then this is power, 5 volts, and that's the 5-volt bus that's going to be used by the Arduino. And I have a 1K pull-up resistor on the collector, just so that it can, that's how it works. So basically what it's going to do is when it's not conducting the transistor, in other words, when the LEDs aren't lit up, so there's no cosmic ray signal, this transistor is not going to conduct, and it's going to be at 5 volts. And when the LEDs are lit up, the transistor is going to conduct, and this is going to be at ground. So that's how it works. It's sort of basically an inverter, but it also isolates. So it allows me to use a separate non-mains earth referenced 5 volts system, which is coming from that plug pack right there for the moment. And so there's a few interesting things I noticed with this. The op amps, comparators, high-pass filters are all the same, power supply is still the same, cosmic arrays are still the same, scope still the same, power supply is still the same. One thing I noticed that's really important, though, is to shield the cosmic rays. Without shielding, the amount of noise is just ridiculous. You need to shield, and you need to shield a lot. So you can see it's almost all encased in shielding. And this is what it looks like. I haven't drawn the peak detector in here. I have the resistor, as you can see, on the opposite side, but that doesn't matter. Pull-up resistor on the collector and grounded emitter, and that's where the signal out is coming. And so basically it's a tiny little blip downwards. Interesting thing I found is that obviously there's a lot of cosmic rays. So with the way that I have the comparator tuned now, we're getting many pulses per second. Again, this is where it'd be helpful to have a digital scope, is because you could see all the pulses over time instead of having them just flashed on an analog scope and they're gone where you can't count them. And then there's very few pulses coming out of this opto-isolator. And I'm not sure why. I don't know if there's internal capacitance preventing it, because it's staying at the high rail and it's going low for about 50 microseconds. And that only happens rarely on very few of the pulses coming out of the peak detector. And I don't know why that is. It seems to work fine, but I don't know if it's just a random correlation or not, which is what makes me nervous, because if it's only on the super high energy ones above a specific point, that's fine with me. But if it's just random, then that means that there's no actual data being produced. I'm just getting random numbers. I've made a fancy random number generator. So that's what worries me, and it may happen that I'm just going to put a voltage divider on the end of the peak detector, which would sort of make an RC filter as well. So I may need to put another op amp there and put a voltage divider just to get the voltage down, have the microcontroller and the rest of the system mains earth referenced as well. I don't want to do that though. I'm confident in this thing, and this is where having a digital scope would really help, because I could actually see the correlation, whereas an analog scope it flashes and it's gone. So, well, let me show you what I mean, essentially. But that's the work I've done so far. The peak detector is working perfectly. No problems there. I have no plans to change that. This Opto-isolator, however, could be tweaked. And I also have the base. They brought out the base of the pin to the Opto-isolator. That's not connected for this one. See the output of the peak detector. So you can see the pulses go up, and then they ramp back down again. You can see there's quite a few of them. If we just make our triggering a little bit better, hopefully you're seeing all of these, and the camera scan isn't preventing this. If we do like this, I don't know what those vertical lines are here. This is a trick that I use a lot. And then you can just, if you speed it up a little bit, you can see basically only when it comes above the screen. Sorry if it's not focused in properly. I might put it just below the camera. Now you can see when it comes right into frame. That's what it looks like, and this is what it looks like normally coming right out of the peak detector. And this is what it looks like coming out of channel 2. So you can see those dips down. I don't know how well they're appearing on camera. If I just put that slightly out of frame at the top. This is now about 5 volts of division. So I don't know if you can see those random peaks or if toning it down would help. I probably can't see the dips down at that point then. I might have to exaggerate this a little bit. So this is now a volta division, so it should go down pretty far. And you can see those spikes downward are the cosmic rays entering it. But now if we turn it on dual mode, okay, and we get those spikes and we make it so that the lines are overlaid, right? So now anything going up should have an exact correlation to anything going down. Maybe just speed up the sweep speed a little bit. And as you can see, a lot of it, there is no, especially on the little ones, I think there is nothing going down. I'll have to review this footage and maybe capture a few screen captures. But it would appear to me that a lot of them, it doesn't go down on, and the signal doesn't dip. So maybe it just requires a super high energy one coming out of the peak detector, which is fine with me if that's the case, which is maybe what it looks to be now. But so that's I think that's what it is after looking at this for more time, is that it just requires a higher energy signal coming out of the peak detector to actually make it all the way through. As you can see, there's comparatively almost no noise on the signal. And to give you an example, these ones going up are 5 volts a division, and going down we're at 1 volt per division. So 5 volts is ideally right. Okay, so this line that my fingernail is on is minus 4 volts. So basically the bottom of the camera screen is, sorry, not minus 4 volts, is 1 volt. So it's a volt a division going down and 5 volts a division going up. Maybe I can get a bit more zoom there. So that's that. If I can speed up the sweep speed a little bit, you can see for a lot of them, maybe that's too fast. interesting way to look at it. I don't know if you can see it going down or not here on the camera. You can definitely see it going up. But when it goes up high enough, it goes down as well. I don't know. I think it's a height issue. I'm just wondering, wanted to show you guys. I have yet to hook this up to an Arduino to see how well the Arduino, I believe these pulses are about 50 microseconds. So I don't know how well an Arduino can process something that fast, if it can actually read it. I'm going to put it on interrupt and see how many it's counting per minute. So you get its counts per minute on these cosmic rays above this certain energy level that's set by the comparator, by the drop of the peak detector, and by somehow the opto-isolator combined, because you can see these little pulses that are 5 volts a division aren't getting through the opto-isolator. I don't know if that's because I've chosen a 470 ohm resistor on the input of the opto-isolator, and the LED's not conducting enough, or what, but it appears that it only triggers down on the high energy cosmic rays, and that it only goes down for the peak, essentially. So the drop that I'm having on the peak detector, you can see that characteristic peak detector thing where the capacitor discharges, doesn't seem to have much an effect on lengthening it because it stays up high for so long. So I have yet to see if I need to increase that capacitance to help the Arduino more easily read those spikes down, if that's fast enough or not. We have yet to see. So I'll probably put the capacitor in a socket on the board and finalize all this up by soldering it, just to make sure, just so I can change the capacitor value in case the Arduino can't read those pulses going downwards off the scope. But it seems that only the really high energy ones actually get through. So this is the end result. This is just channel 2. So maybe I'll move this up a bit so you can actually see the whole pulse. But that's the end result of everything. Those down pulses are cosmic rays, and this is directly what's going into the microcontrollers, this signal. So I believe I'm finally done. Sorry if I've rambled on a bit in this video, I feel that way. But I'm a little tired. No excuse. Not excuse, really, but feel free to bash on me for it. But this is the end result. I have the light running in the other half of the room next to me, though, but there doesn't appear to be much noise. Like I said, that the shielding is taking care of most of the noise, light noise as well. The foil tape is pretty good at keeping out light, keeping it light sealed. So I'm pretty sure this is final. This is what's going to go directly into the Arduino to read and data log to. Well, actually, I think this occasion calls for sort of the history and future of the cosmic rays. So. All these cosmic rays are playing in the background for you here, and hopefully you're going to see some of those down spikes. I haven't seen one in a while. Not always when it flashes is that a down spike. You actually have to see something going down. It could be flashing just because it thinks it's triggering on something.